Bismillah ar-Rahman ar-Rahim. Matrix A has zeros on the main diagonal. All the other elements are either 1 or -1. Can we construct matrix A so that it is not invertible? If yes, what is an example of such construction? If n is equal to 1, we have a 0 on the main diagonal. This is not invertible. If n is equal to 2, this element is 0, that element is 0. This can be plus or minus 1. This can be plus or minus 1. The determinant of the matrix is 0 minus the product of these two off-diagonal elements, which is either 1 or -1. The determinant itself is either 1 or -1. It's never equal to 0. We can never have a 2 by 2 matrix with zeros on the main diagonal, ones and -1s elsewhere, that is singular. This matrix must be invertible. If n is equal to 3, can we make this matrix singular? The easiest way to do this is to have in each row +1 and -1. I can put here 1 and here -1. I can put 1 here, -1 there. Let's have the third row as -1, 1, and then 0. This matrix is singular. If D is the all 1 vector, matrix A times vector D is equal to the all 0 vector. The sum of the 3 columns is the all 0 vector. We have a linear combination of the columns that is equal to the all 0 vector, and vector D is not the all 0 vector. This means that the columns are linearly dependent. The matrix is rank deficient. Its determinant is equal to 0. The matrix is singular. Based on this construction, we can say that if n is odd, matrix A can be made singular by having an equal number of 1s and -1s in each row. Each row has an odd number of elements. If we are talking about the jth row, element jj is 0. Then we have n-1 elements. n-1 is even. If half of those elements are set to 1 and the other half are set to -1, then the sum of the elements on each row is 0. The matrix times the all 1 vector is equal to the all 0 vector. The null space of the matrix is non-trivial. The matrix is rank deficient. Recall the rank nullity theorem. The rank of the matrix plus the dimension of the null space is equal to the number of columns. If the dimension of the null space is strictly greater than 0, then the rank of the matrix is strictly less than n, so that their sum is equal to n. If the matrix is rank deficient, it is not invertible. If n is even, we have just investigated one case, and it was impossible to construct matrix A such that it is singular. Can we prove that for every even n, A must be an invertible matrix? Let's compute the determinant of matrix A. In the 2 by 2 case, that was easy. But in the general case, any off-diagonal element is either +1 or -1, and the exact value of the determinant will depend on the configuration of 1s and -1s inside the matrix. The trick here is to compute the determinant of A modulo 2. The idea is that 1 is congruent to 1 mod 2, -1 is congruent to 1 mod 2. If we write matrix A modulo 2, then we have the zeros on the main diagonal. Every off-diagonal element will be equal to 1. Matrix A mod 2 is equal to D transpose. D is the all 1 vector. Its transpose is a row vector of 1s. And if we multiply D by D transpose, we get a matrix that is an all 1 matrix. Because the matrix has zeros on the main diagonal, we need to subtract identity of size n by n. This is the matrix if we take each element modulo 2. Note that from the properties of modular arithmetic, computing the determinant of A mod 2 is equivalent to taking each element of the matrix mod 2 and then computing the determinant. Alpha plus beta mod m is equal to alpha mod m plus beta mod m. Alpha beta mod m is equal to alpha mod m times beta mod m. The determinant of A mod 2 is equal to -1 to the power n, the determinant of the identity, minus D transpose. This is the all 1 n by n matrix. This is an application of the rule that the determinant of a scalar k times matrix A is equal to k to the power n times the determinant of A. What is the determinant of this matrix? Let's apply Sylvester's determinant identity. If matrix C is of size j by k, matrix D is of size k by j, then the determinant of identity of size j by j plus CD is equal to the determinant of identity of size k by k plus DC. Let's employ this result in our case. We are interested in the determinant of identity plus minus D transpose. This is of size n by 1, this is of size 1 by n. This determinant is equal to the determinant of identity of size 1 by 1, which is just 1, plus d transpose minus d. This is the determinant of 1 minus d transpose d. This is a matrix of size 1 by 1. It's just a scalar. This determinant is equal to 1 minus d transpose d. If we have a row vector of 1s times a column vector of 1s, this inner product is 1 times 1 plus 1 times 1, and so on. This inner product is equal to n. The determinant of A mod 2 is equal to minus 1 to the power n times 1 minus n. If n is even, then the determinant is congruent to 1 modulo 2. The determinant is odd. In this case, the determinant of A is never equal to 0. If n is even, a matrix with zeros on the main diagonal, plus and minus ones elsewhere, is guaranteed to be invertible. It cannot be singular.